Hi, everybody, and welcome to our first lecture for statistics. We're going to go over 1-1. It's mostly just a bunch of definitions, but I thought I would start here. Key concept. The process involved in conducting a statistical study consists of prepare, analyze, and conclude. Basically, that's what we're doing. We're getting data, and we're going to go over that. And we're going to use that data to analyze it and make some types of conclusions about it. Statistical thinking involves critical thinking and the ability to make sense of results. Statistical thinking demands so much more than the ability to execute complicated calculations. In this class, we won't be doing a lot of complicated calculations. More we'll be doing analyzing and concluding. What is data? Data is a collection of observations, such as measurements, genders, or survey responses. For example, you want to know what is the salary range of students who graduate from FAU? That would be data. We would collect data, and then we would do something with that data. The data is the collection of certain observations. Statistics is the science of planning, studies, and experiments. Why is that first? Because you have to plan what you're doing. Say, for example, you wanted to find out what the favorite TV show in the United States is this year. Well, how are you going to do that? You could call all your friends and ask them what their favorite show is, but would that actually give you any idea of what the country's favorite show is? Probably not, because they would just be your friends. The planning part is very important. After we plan how we're going to get the data, then we get the data, we organize it, we summarize it, because I don't want to just hand somebody a piece of paper with all the different names of all the different TV shows they watch, because that would be very hard to read. We would have to organize it in such a way that when we give it to the next person, they understand what it is we did. That's the organizing and summarizing. And obviously presenting, analyzing, and interpreting this data and drawing conclusions based on what data we get. This all is what statistics is. Now, when we talk about population, we are talking about everybody. If I wanted to find out what students at FAU's favorite class is, the population is students at FAU. We would have to actually ask every student at FAU what is their favorite class. That would be the entire population. We could say the population of the country. We could say the population of our class. But when we say population, we mean the total amount of them. Let's read the definition. The complete collection of all measurements or data that is being considered. Typically, a population is the complete collection of data that we would like to make inferences about. We really need to talk to every single person if we want to get information about the population. When we talk about a census versus a sample, a census is the collection of data from every member of a population. When we do the census in the United States, I think once every 10 years, and we literally want every single person in the United States to answer that. The census has to do with the entire population. Now, a sample, let's say I wanted to find people's favorite classes at FAU. I could just say, well, there's no way I can find and talk to every single person at FAU. Maybe we'll take a subset or a sub collection of members. Maybe we say instead of everybody at FAU, we just randomly grab 500 people and we ask them the question and we'll get an answer. That sample is a part of the population. That sample, if it's random, We should be able to draw inferences from the sample about the entire population of the university. Let's look at an example. In the journal article, Residential Carbon Monoxide Detector Failure Rates in the United States, it was stated that there are 38 million carbon monoxide detectors installed in the United States. When 30 of them were randomly selected and tested, it was found that 12 of them failed to provide an alarm in hazardous carbon monoxide conditions. In this case, what is the population and what is the sample? Remember, the population was everything. We can say the population is the 38 million carbon monoxide detectors in the United States. Now, that would be really hard to talk to 38 million people who bought these carbon monoxide detectors. So instead of doing that, what we're going to do is find a random sample. And we're going to find out from that random sample what happened. The difference between the population and the sample is that the sample is 30 out of the 38 million carbon monoxide detectors. We're going to pick 30 people just randomly. The objective is to use the same sample data as a basis for drawing a conclusion about the population of all carbon monoxide detectors. If we have 30 and 12 of them fail, that's a lot. If we have 38 million, we're going to have millions and millions, probably somewhere around 18 million of them failing. We could calculate the exact amount. How would we calculate this exact amount? Well, let me show you. If we know that 12 out of 30, this is the part out of the whole, which gives me 0.4. What does that mean? If we want to change that to a percentage, we take this number and we multiply by 100, which gives me 40%. 40% in that sample of all the carbon monoxide detectors that were tested failed. That's a big percentage. That means if I sell 38 million, let's say I sell 38 million, and I want to know how many of those are going to fail, I'm going to multiply that by equivalent decimal amount, and I would get 15,200,000. If I own this company and out of 38 million that I sold, 15 million fail, something's wrong with our carbon monoxide detectors. What we did was we found the percentage from the sample, and then we said, okay, if that's the right percent, how many are going to fail out of all of them? It would be this 15 million. Pleasure boats and manatee fatalities from boat encounters. Here we have pleasure boats in tens of thousands. So that means that this is 99 10,000s or 990,000. Out of that, 92 manatee died. And then we can look at the same amount of pleasure boats, 73. Little less pleasure boats, 90, and so on. This is our table. The table includes the number of registered pleasure boats in Florida in the tens of thousands and the number of manatee fatalities from encounters with boats in Florida for each of several recent years. Now, they're not telling me what years these are. Doesn't matter. The format of the table suggests the following goal. Determine whether there is a relationship between the number of boats and the number of manatee deaths from boats. And we really just want to know, the more boats that are in the water, does that mean we're going to have more and more manatee fatalities? The source of the data. The table includes the number of registered pleasure boats in Florida. Where did we get that information? The data in the table are from the Florida Department of Highway Safety and Motor Vehicles and the Florida Marine Research Institute. Our sources appear to be reputable. And what is our sampling method? The data were obtained from official government records known to be reliable. The sampling method appears to be sound. And because they're official government records, they must be reliable. My sampling method was good. We also have something called a voluntary response sample. A voluntary response sample or self-selected sample is one where the respondents themselves decide whether to be included. I'm sure you've seen them. You get them in your email, you get them online. All of a sudden, something pops up and it says, "Can you please fill out this survey?" And it's your choice whether or not to fill out the survey. That's called a voluntary response sample. Do you think that would be a good way to get information about a certain subject? Just think about it for a minute. It wouldn't be, right? Because what if the survey was, "How do you feel about surveys?" Well, the only people that would answer are fine about surveys. And everybody who doesn't like surveys would not answer it. It's not a very reliable way to find a. The following types of polls are common examples of voluntary response samples. By their very nature, all are seriously flawed because we should not make conclusions about a population on the basis of samples with a strong possibility of bias. Internet polls in which people online can decide whether or not to respond. Not a very good way to find a sample. Mail-in polls in which people can decide whether to reply. Telephone call-in polls, in which the newspaper, radio, or television announcement asks that you voluntarily call a special number to register your opinion. That's why voluntary response samples are not really the best type of ways to sample for statistical data. Nightline asked viewers to call with their opinion about whether the UN headquarters should remain in the United States. Viewers then decided themselves whether to call with their opinion. 67% of 186,000 respondents said that the UN should be moved out of the United States. That's one way that we did the survey. In a separate independent survey, 500 respondents were randomly selected and surveyed, and 38% of this group wanted the UN moved out of the United States. Which one do you think would be more reliable? Here we had 186,000 respondents, and here we only have 500. And the numbers are very, very different, aren't they? 67%, 38%. Why are they different? The two polls produced dramatically different results. Even though the Nightline poll involved 186,000 volunteer respondents, the much smaller poll of 500 randomly selected respondents is more likely to provide better results because the far superior sampling method. What was the difference? The Nightline one is voluntary, and the independent survey randomly picked 500 respondents. How many of you guys watch Nightline? We may have only older people. We may have mostly white people. We may have mostly Christians, or we may have mostly men. There's many things that go into it that we don't know who's calling in. But here in the independent survey, even though it was only 500 people, they were randomly selected. We have people of all ages, of all races, of all sexes. The 500 respondent one would definitely produce a more correct result. Randomly selected respondents is more likely to provide better results because of the far superior sampling method. How we get the data is very important. After completing our preparation by considering the context, source, and sampling method, now we have to start to analyze the data. We can graph and explore. An analysis should begin with appropriate graphs and explorations of the data. After we graph data, we can see, does it have a trend? I'm going to draw a graph. This would be education. This is the x-axis, remember, and this is salaries on the y-axis. And let's say our data looks like this. This is 6th grade. This is finished high school. This is finished 4 years of college. This is got your master's degree. And these are the salaries. If all you completed was 6th grade, let's say you make $10,000 a year. If you finish high school, then maybe you make $30,000 a year. If you went to college, maybe you make $50,000 a year. We can see there's a trend here. They're all gathering around this line. We can see that the more education you have, the higher the salaries you'll probably earn. So that would be an example of graph and explore. Apply statistical methods. A good statistical analysis does not require strong computational skills. A good statistical analysis does require using common sense and paying careful attention to sound statistical methods. We will not be doing a lot of calculations. We have StatCrunch, which I will show you how to use, and that will be doing most of our calculations. Don't worry about the math. What it means is more important. And conclusion. The final step in our statistical process involves conclusions, and we should develop an ability to distinguish between statistical significance and practical significance. Statistical significance. Getting 98 girls in 100 random births is statistically significant because such an extreme outcome is not likely to result from random chance. Basically, we have girls, we have boys. It's probably about half and half in general. 98 out of 100 is definitely significant. How about getting 52 girls in 100 births? It's not statistically significant because that event could easily occur with random chance. Let's say I had 10 groups of 100 women. There's a chance that one of those groups had at least 52 girls out of 100. Another group could have 45. Now, practical significance. Is it possible that some treatment or finding is effective, but common sense might suggest that treatment or finding does not make enough of a difference to justify its use or to be practical? Here's an example. Procare Industries once supplied a product named Gender Choice that supposedly increased the chances of a couple having a baby with the gender they desired. In the absence of any evidence of its effectiveness, the product was banned by the Food and Drug Administration as a gross deception of the consumer. Suppose the product was tested with 10,000 couples who wanted to have baby girls. The result consists of 5,200 baby girls born in the 10,000 births. This result is statistically significant because the likelihood of it happening due to chance is a really, really small percent, 0.003%. Chance doesn't seem like a feasible explanation. That 52% rate of girls is statistically significant, but lacks practical significance because 52% is only slightly higher than 50%. Couples would not want to spend the time and money to increase the likelihood of a girl from 50% to 52%. If it was 50% to 75%, maybe it would be. Now, they're also noting that in reality, the likelihood of a baby being a girl is actually less than 50%, not 50%. 52%, it's still less than that 5% difference that we're saying we would need to have it be statistically significant. The likelihood of an event occurring by chance is 5% or less. If it was over 5%, it would have some statistical significance. Whether or not it has practical significance is different. If the medicine costs $5 or $10 and you could go buy it at the grocery store, maybe be worth trying. But if it costs $1,000 or $2,000, you'd have to go to your doctor. It might not be practically significant. Analyzing data, potential pitfalls, misleading conclusions. When forming a conclusion based on a statistical analysis, we should make statements that are clear, even to those who have no understanding of statistics and its terminology. Basically, you want to be able to say something that means something to somebody who doesn't actually know statistics. 5% of all people who visit Florida do it in the month of January. I could understand that. You could understand that, even if we didn't have any statistical knowledge. Sample data reported instead of measured. When collecting data from people, it is better to take measurements yourself instead of asking subjects to report results. Let's say you're asking people their weight. Definitely better to have them step on a scale than to ask them how much they weigh. Loaded questions. If survey results are not worded carefully, the results of a study can be misleading. And like say, for example, I went and I asked everyone in the class, do you think that your grade point average is high or low? Well, that's not worded very well because I could have a 2.5 grade point average and think that that's high because in high school I had a 2.0. Or I could think that a 3.5 grade point average is low because in high school I had a 4.5 grade point average. If I'm asking a question that's not very clear, I probably will get misleading results. Order of questions. Sometimes the survey questions are unintentionally loaded by the order of the item being considered. If you ask certain questions in a certain order, it's almost like you're leading somebody to a conclusion. Again, that's something you have to be really careful about. Non-response. A non-response occurs when somebody either refuses to respond or is unavailable. Well, that's a person that we can't really use in our survey, but that may be one of the people that we randomly picked. Percentages. Some studies cite misleading percentages. Note that 100% of some quantity is all of it. But if there are references made to percentages that exceed 100%, such references are often not justified. 100% of something is all of it. If I want to know what 100% of my salary is, it's my salary. However, what if I said 200%? Well, how can I have 200% of my salary unless I'm getting a raise? The point of this whole entire thing is when you're using certain words, make sure that you understand what it means. And that is really the end of 1-1. Thanks for listening.